Hello and welcome to my virtual presentation. In the next 20 minutes or so, Nirupam Gupta, will present my joint work with Professor Nitin Vaidya on the topic of fault tolerance in distributed, multi-agent distributed optimization, with emphasis on the case of redundancy. This part of our work on fault tolerance was submitted to the PODC conference, this year's PODC conference that, as we all know, is being held virtually due to the ongoing pandemic crisis. On introducing the traditional problem of multi-agent distributed optimization, I will define the problem of fault tolerance, the requirements of fault tolerance, the need for fault tolerance. After doing that, I will present our contributions made in the paper. Now, as far as we know, the work on distributed optimization was actively being pursued in 1980s with John Sitclis pioneering the field with his PhD dissertation published in 1984. In this problem of multi-agent distributed optimization, the system comprises of multiple agents. In our case, we consider n number of agents. Each agent has a cost function represented by Q in this case that depends upon a global variable represented by W. The objective of the agents is to compute an optimum point such as W star that minimizes the aggregate of all the agents' cost functions. So far, there have been a lot of algorithms, distributed algorithms that apply to both server agent architecture and peer-to-peer architecture. In practice, this abstract problem finds many applications. For example, consider the case of multi-agent rendezvous problem, where W represents a location and the cost Qi of agent I represents the transportation or physical cost for that agent to move to that location W from its current location. W star, that's the minimum point, global minimum point, is a meeting point for all these agents that minimizes the aggregate cost for all the agents involved. In context of machine learning, Qi represents the expected loss of agent I for a learning parameter W fixed by a learning model, depending upon the local data sets held by agent I. And W star is essentially the optimal learning parameter that optimally fits the learning model over all the collective data sets being observed by all the agents in the system. The model of distributed optimization can also apply to classification or hypothesis testing, multi-agent hypothesis testing settings, where you have multiple agents or sensors, you may call, that are trying to identify a single common object. Each agent observes the object partially, as in this case, a large object that is an elephant being observed by smaller agents, each of them observing different parts of it, and collectively they would like to identify the object. So Qi is an error for hypothesis W, let's say, made by agent I, and W star then is the true identity of the object being collectively observed by the agents. Now, most work on distributed multi-agent optimizations has been focused on fault-free settings, where all the agents are free from faults, that is, they honestly follow the prescribed algorithms. We consider a setting where some of the agents, specifically at most F out of N agents, are Byzantine faulty. Now, obviously, it is quite clear that because these Byzantine faulty agents may be sending incorrect information or concocted information corresponding to malicious cost functions. to prevent the non-faulty agents from solving the optimization problem, the distributed optimization problem. So it's clear that in this particular case, it, it it's not reasonable to try to solve the original distributed optimization problem, because why would you like to minimize the aggregate that involves incorrect cost functions? A reasonable goal would be to compute a point that minimizes the aggregate of all the non-faulty cost functions, as shown here in mathematical terms. The challenge, of course, is that the identity of Byzantine faulty agents is a priori unknown, is hidden, and these Byzantine faulty agents are assumed to be omniscient, meaning that they have prior information of all the other non-faulty agents' cost functions. So they can really send clever, incorrect information to prevent all the non-faulty agents from solving this fault tolerance problem. This problem of fault tolerance was introduced by Lilly and Nitin in their PODC 2016 paper, where they proposed an algorithm that would minimize the weighted aggregate of the honest cost functions. In our original fault tolerance requirement, we want to minimize the uniformly weighted aggregate of the cost of the non-faulty cost functions. They propose an algorithm, they propose a solution where you can minimize the weighted aggregate of all the cost functions. As I've just said, so our minimizing the uniformly weighted aggregate, we'll call it as exact fault tolerance. Minimizing the weighted aggregate, we call it approximate fault tolerance, because these weights may be non-uniform. Now, in their 2016 paper, Lilly and Nitin showed that you cannot achieve exact fault tolerance, meaning these weights cannot be uniform unless you have some sort of redundancy in the system. Now, in 2017, a group from EPFL, Blanchard and colleagues, showed that, well, in case of homogeneous distributed learning problem, you can actually compute the exact fault tolerance because the agent's cost functions are identical in expectation, and therefore it's the redundancy, there's just too much redundancy in the system, and it should be possible even if the gradients, even if the agents are sending stochastic information about their cost functions to solve the exact fault tolerance problem. Since then, since this 2017 paper by Blanchard, there has been an explosion of work on fault tolerance in context of learning by assuming various stochastic properties regarding agents' cost functions. And most of these works are quite applicable in machine learning setting. However, in case of deterministic, the more general optimization setting, this question of what is the precise characterization of redundancy under which you can solve the exact fault tolerance problem remain unknown. And this is what motivated us for the first key contribution of our paper, where we explore the exact characterization of redundancy needed for the system to solve, for the non-faulty agents to solve the exact fault tolerance problem. Now, specifically, we show that exact fault tolerance is achievable if and only if the agents have 2F redundancy. What 2F redundancy means, as defined here, is that the minimum of the cost functions of honest agents should also be a minimum of any n minus 2F honest agents aggregate cost functions. As shown here, S is just a subset of the honest agents of size n minus 2F, and whichever point minimizes this aggregate on the subset of costs should also minimize the aggregate of honest costs, and vice versa. Now, this is a very strong condition, and it's quite natural to think that it may be a very contrived condition that may not hold in practice. However, that's not the case. We have seen in practice that 2F redundancy holds quite naturally in a lot of systems. For example, in homogeneous distributed learning problem, because the non-faulty agents cost functions are identical in expectation, 2F redundancy holds naturally. In case of distributed classification, well, for example, in this particular case of identifying an elephant, you do not need all the sensors to observe the object. You could observe the object from just a few of the sensor observations, as shown here. Either you can just have these four or these four, and you can still identify that it's an elephant. So in practice, it does hold pretty much in practical systems. So now that we have established the need for 2F redundancy, we move on to finding a distributed algorithm that would actually solve this problem of exact fault tolerance. And to do so, we wanted to design an algorithm that is minimally invasive to the existing standard algorithms for solving this problem. And so we review the standard method of gradient descent. So gradient descent is a well-known iterative method where you are given a cost function and you're trying to compute a minimum of that cost function. You start with an estimate of a minimum, let's say W0. You compute the gradient of that cost function at W0, and you update to W1 by moving in the opposite direction to the gradient of the cost at W0. You do the same at W1 and at W2 and W3, and you keep doing this iteratively. And if the cost function is convex and the gradients are Lipschitz continuous, then we know that eventually you are going to compute a point that minimizes this cost function. Now, this distributed variant of gradient descent is quite natural in server architecture setting, where the server, let's say, starts with maintains these estimates of the optimum. They broadcast these estimates to the agents. Each agent computes the gradient of their local cost function and sends these gradients to the server. Now the server takes aggregate of all the gradients received from the agents and update its current estimate in the opposite direction, as shown here. I'll shortly discuss what the tilde sign is. Now coming to the faulty setting, where some of the agents are faulty, so they may not be sending you the correct gradients, the server correct gradients. So in this particular work, we consider that the server is trustworthy, meaning the server is free from faults. Now, let's say the server, because the faulty agents may be sending arbitrary vector to the server, the traditional gradient descent algorithm is rendered ineffective in presence of Byzantine faulty agents. So how can you take care of such Byzantine faulty agents and distributed gradient descent? So the solution is very simple, and it can be described in like 4 words, which is filter the received gradients. And the idea actually goes back to the original paper on fault tolerance by Lilly and Nitin, where they proposed a truncated mean or trim mean based gradient filter that worked pretty well for the case when the gradients were scalars. We in our paper consider a more general setting where the gradients can be of high dimension. And so we were not able to extend those trim mean scalar gradient filters quite as well, quite nicely, I should say, to the case of high dimension gradients. Now, our proposed gradient filter, we call it comparative gradient clipping, depends on filtering based on the Euclidean norms of the gradients, which is, in common language, the magnitude of these gradients. So the step one, as shown here, is the server receives all the gradients from the agents, takes the norm of those gradients, and sorts these gradients according to their Euclidean norms. So I1, as shown here, is the agent that sends the smallest gradient. IN is the agent that sends the largest gradient. Upon doing that, the server rescales the gradients that have the largest F norms. F, recall, is the maximum number of Byzantine faulty agents in the system. So as shown here, you rescale the magnitude of these larger gradients. And once you have done that, you aggregate you aggregate these rescale gradients, which is as the tilde sign shown here. Now, bounding this kind of rescaling of the gradient norms bounds the magnitude of the faulty gradients, and it mitigates the detrimental impact of faulty agents on the distributed gradient descent algorithm for the fault tolerance in distributed optimization. So we have shown in our paper that distributed gradient descent method with CGC gradient filter guarantees exact fault tolerance if 2F redundancy holds, which is anyway a necessary condition, as we have already established. The cost function, the gradients of the cost functions are Lipschitz continuous, which is fairly standard in practice if you are aware of certain applications, as we have presented early on in this presentation of distributed optimization. Third assumption is that the aggregate cost of all the non-faulty agents is strongly convex. Now, this is a slightly stronger assumption than usually what we see in practice. However, you can make a non-strongly convex cost function strongly convex by techniques like one-shot regularization or iterative regularization, and it's fairly easy to extend algorithms that are applicable just for strongly convex cost functions to only convex cost functions. Now, the fourth assumption here is the boundedness of the fraction. So besides 2F redundancy, we also need the fraction of the faulty agents to be bounded. Now, this is, as we see, is slightly non-optimal. However, we are not aware of any gradient filter that achieves fault tolerance just by assuming 2F redundancy and nothing else about the fraction of faulty agents. There is still an open problem. Can you even have a gradient filter that obtains exact fault tolerance by just assuming 2F redundancy and nothing else on the fraction of faults? Now, other shortcomings, obviously, as I've mentioned, is the strong convexity of aggregate cost function. So far, in our paper, in the paper submitted to PODC, we consider a complete peer-to-peer network or server agent architecture. Applicability is possible. We are working on it currently, but we do not have any neat, nice, clean results so far. Now, the good news is there are many extensions of this CGC gradient filter. You can apply it for gradient descent method in partially asynchronous systems where the response of agents is not synchronized with the server. There's latency in the system. the gradients that you receive from the agents are from older estimates. So that's okay as long as those estimates, as long as these delays are bounded. Another easy extension of our proposed gradient filter is to stochastic gradient descent methods that are fairly common for distributed learning settings, where you only send some approximation, stochastic approximation of the true gradients of your cost functions instead of exact true gradients. And the third, which is quite important, is extension to approximate redundancy, because in many practical systems, because of system noise, observation noise, data noise, execution noise, communication noise, you may not exactly have 2F redundancy as ideally defined mathematically in our previous slide. Now, but what you may have is approximate redundancy, meaning the optimum of only n minus 2f honest cost functions may be an approximate optimum of the honest cost functions. So we have seen that it is still possible to extend this CGC gradient filter for those kind of approximate redundancy settings. And it's applicable to heterogeneous learning as well, like not just homogeneous. Heterogeneous learning refers to the setting where different agents might be observing data points from different distributions and not a common distribution, unlike the homogeneous learning. Now, the details of the work that I have presented in this talk can be found in these online archive reports highlighted here. So we started doing the work in January last year. That was our first report uploaded in March 2019 on Byzantine fault-tolerant distributed linear regression. We considered first the linear regression problem, and then we extended the work to general convex cost functions as presented in our paper. And recently, just like 3 or 4 months ago, I think, we have extended our work to independent cost functions where you do not have redundancy, 2F redundancy or in the cost. And in that particular case, we redefine basically our fault tolerance requirement, because you cannot achieve exact fault tolerance, but you can achieve something we call as approximate fault tolerance. Something similar to what Lily and Nitin proposed in their 2016 paper, but with a slightly different flavor. Now, we have also considered a fault tolerance setting in parallelized distributed learning, parallelized machine learning settings, where the agents are basically workers that are computing the gradients or stochastic gradients for the server, which is assuming the role of a master. And we have proposed an optimum reactive redundancy based coding scheme for tolerating such faulty workers in the system. And we have also considered as I said, the extension of our CGC filter can be made to stochastic gradient settings, which was shown in our 2019 paper presented at Allerton conference on by considering a special case of linear regression. However, recently we have seen that it can extend to general machine learning settings where the cost functions need not be quadratic or least squares, or could be arbitrary convex functions. Now, by that, I would like to conclude my thought. Before we end, I would like to thank our sponsors, the Army Research Lab and the National Science Foundation, the grant numbers as shown. Thank you very much for listening. If you have further questions, further comments, you can always email us. Our email IDs can be found on these web pages and are also included in the paper. So thank you very much and enjoy the rest of the conference. Take care.